Dr. P here. At this point, you're probably thinking to yourself, if work is just talking about the amount of energy that's put in or taken out of a system, I bet there's a way to relate the work to the velocity of an object. And you're right. So if I take this idea that net work is the net force times the change in position or the displacement or the distance that it goes, I can say, okay, well, the net force by Newton's second law is just mass times acceleration. Okay, now bear with me. We need to do a little bit of algebra here. Okay, so you should remember this equation. Velocity final squared is velocity initial squared plus 2a delta x. Notice I have an a delta x here, and I have an a delta x here. So what I want to do is solve for a delta x and then plug it into this equation. So I get velocity final squared minus velocity initial squared over 2 is a delta x. So I'm going to plug this right in here. So that gives me the net work is mass times velocity final squared minus velocity initial squared over 2. This should start looking like something because I have a divided by 2, or 1/2 times the mass times the final velocity squared minus 1/2 times the mass times the initial velocity squared. I just multiplied this all out. Okay, this is the final kinetic energy, and this is the initial kinetic energy. So if I take the final kinetic energy subtracted by the initial kinetic energy, that is just the change in kinetic energy. So the net work done is the change in kinetic energy. This is called the work energy theorem, or the work-kinetic energy theorem. The interesting thing, or the important thing with this, is that this is valid when the force is not constant, or you have a curved path. So kinematics, we can only use those if the acceleration is constant, meaning you have a constant force. And everything with kinematics is objects going in straight lines, or ways that we can split it into the x direction and the y direction. But this is a way that we can solve more complicated motion problems because all we need to know or find is the work or the change in kinetic energy. So this example should look familiar. Previously, you were asked to find the net work, and if you don't remember that, you can go back in the videos. This time, the question is going to be, what is the final velocity of the box? And so if before you've learned the work-kinetic energy theorem, where work net is the change in kinetic energy, before you learned that, you would need to sum the forces in the parallel direction and then set that equal to mass times acceleration, and then use a kinematic. And we'll do that at the end. Now we can say the total work is equal to the change in kinetic energy. And so because we found the net work previously as 56 joules, this is going to be a fairly simple problem. Okay, so 1/2 mv final squared minus velocity initial squared. That is the change in kinetic energy, and our net work is on this side. So we need the mass. The weight is 225 newtons, so the mass will be 22.5 kilograms. In this problem, it says that the initial velocity is 0.75 meters per second. So we get 56 joules is equal to 1/2 times 22.5 kilograms times the final velocity, this is what we're looking for, minus the initial velocity of 0.75 meters per second squared there. There's a lot of math here, so just bear with me. This will be 11.25 times the velocity final squared minus, we square this and then we'll multiply it by this 11.25, and we get 6.33-ish for this second term, 56 joules. Move this to the other side, 62.33 equals 11.25 times the final velocity squared. So divide both sides by 11.25. We get the final velocity squared is equal to about 5.5. So we'll take the square root of both sides, and we get a final velocity of about 2.4 meters per second. Now that was a lot easier than summing the forces, which we're going to do right now. The good news is in the previous video, we actually found the sum of the forces in the parallel direction. If you remember, that's negative force of friction minus Fg parallel plus the force applied. And when we did that, we got 9.4 newtons. So 9.4 newtons is the mass, which is 22.5 kilograms, times the acceleration. Remember, this is Newton's second law, F net equals ma. So we'll take 9.4 divided by 22.5, and we'll get our acceleration of 0.42 meters per second squared. Then we can use this equation, velocity final squared is velocity initial squared, plus 2a delta x, this is our change in position, remember, of 6 meters, times, so our initial velocity is 0.75 meters per second squared, plus 2 times 0.42 meters per second squared. And so we plug this into our calculator, and we actually get the same answer here. 5.6 meters squared per seconds squared is our final velocity squared. Square root both sides, and you end up with the same velocity.